Hello student, in this lecture we will solve one of the example of separation of variable. So in the last lecture we already solved one example of Laplace's equation in Cartesian coordinate system. Now in this lecture we will solve a new partial differential equation which is Helmholtz equation in Cartesian coordinate system. So let us see one example. The example is write down the Helmholtz equation in Cartesian coordinate system and separate the variable in it to obtain ordinary differential equations. So solution of this Helmholtz equation is, so we have to consider one function, that is here we consider psi with a function of three independent variables in Cartesian coordinate system, which is x, y and z. So the general form of Helmholtz equation is del square psi plus k square psi equal to 0. Now, this Laplace del square is a Laplacian operator, and in Cartesian coordinate, Laplacian operator can be written as del square by dava x square plus dava square by dava y square plus dava square by dava z square. Now, by using this value of del square, we can write as the Helmholtz equation in Cartesian coordinate system is del square psi plus k square psi equal to dava 2 psi by dava x square plus dava 2 psi by dava y square plus dava 2 psi by dava z square plus k square psi equal to 0. This is what the general form of Helmholtz equation. Okay. So here we can give a number. This is equation number 1. Okay. Now we have to find the solution of this differential equation. Let us consider this is our partial differential equation because this equation is dependent on three variables x, y, z. Okay. So to find out the solution of this Helmholtz equation, we have to convert this equation into the ordinary type of differential equation, and we can easily find out the solution of ordinary differential equations. Okay, now let us solve this partial differential equation, convert into the ordinary type of differential equation. So for this purpose, we have to consider the solution of this equation is psi. Let us assume this solution is the product of three functions which is equal to, that is psi of x, y, z equal to, which is the product of three functions x, y and z, where you can write as this as directly x, y, z. So here x is a function of x is the function of only the independent variable of x only, while this y of y function is only the function of independent variable of y only, and similarly the z of z is the function of independent variable z only. So here we will put the value of psi equal to x, y, z in equation number 1. Okay. So the equation number 1 becomes, so here I will just write equation 1 becomes, so by putting the value of psi equal to x, y, z, our Helmholtz equation becomes like this. Okay, dava 2 x, y, z by dava x square plus dava 2 x, y, z by dava y square plus dava 2 x, y, z by dava z square plus k square x, y, z equal to 0. Okay. Now we will just solve this equation as just this bracket term. So I'll just call it suppose which is equal to some constant. So here I'll just consider that constant is suppose m square. Okay. So this constant becomes m square. So just by rearranging this term or to the left side, so this m square comes to the left side, it becomes plus m square. Okay, and after multiplying with this x with the whole throughout the term, so we get this new equation which is only x dependent. Okay, so this term here is this x is only x dependent while this m square is a constant. So you can say that this is your ordinary type of differential equation. So in this way we get our first ordinary differential equation. Now again, right hand side of the above equation is what? This equation is m square equal to this total term is equal to there. Okay, so this is dependent on y and this dependent on z. Okay, so here what I did, I'll just take this z dependent part to the right hand side. So this new term, so if you see the left hand side of this equation is only the y dependent, this y dependent term is there, while here is the z dependent term to comes to the right hand side. So here I'll just rearranging this term for a simplification. We get this new equation. Okay. So 1 by y square dabba 2y by dabba y square equal to this total term, and this total term I'll just consider equal to, suppose equal to some constant. So this constant equal to, I'll just write n square. Okay. So this n square is also the constant which is called as a separation constant. Okay. So again, therefore you can write as 1 by y dabba 2y by dabba y square equal to minus n square. Okay. So you can say that this LHS of this equation is y dependent equal to constant. So just by rearranging, you will get this equation which is equal to only y dependent equation, which is our second ordinary differential equation. So here I'll just give a number b. Now here again I'll consider this right hand side of this equation. So this equation can be so equal to this, okay, which is equal to minus n square. So here just consider, I'll take this, just removing this minus part, minus sign. So by rearranging, you can write as this equation as, okay, above like this. So here we consider this part, because this k square is a constant, m square is also constant, and n square is equal to constant. So for simplification, just you can just write this total quantity equal to, suppose, one of the constant which is suppose equal to p square. So this equation becomes, you can write as this equation as 1 by z dabba 2 z by dabba z square plus one constant p square equal to 0. So new equation is what? Dabba 2 z by dabba z square plus p square z equal to 0. So this total equation is only z dependent, which is our third ordinary differential equation. So here, if you see over here, this is p square is only the combination of these all constant. So k square is a constant which is from the Helmholtz equation. This m is our separation constant. N square is also the separation constant, but this p square is not a separation constant. It is only the combination of all constant. For a simplification term, for a simplification, we take this constant as like this. Okay. So this is what, there are only two separation constants are there. So here we get type of differential equations. So here is the equation number A, equation number B, and equation number C. So that means we convert our Helmholtz differential equation into three ordinary type of differential equation. Okay, three ordinary type of differential equation, and for this solution we get two separation coefficient, right? Two separation coefficients. I'm sorry, constants, not coefficient, constant. Two separation constants. So here we consider our Helmholtz equation in three-dimensional equation. Okay, that's why it is dependent on three variable x, y, z. So we got three ordinary differential equation and two separation coefficient. Suppose our equation is depends on n variables, then we get n ordinary differential equation and n minus 1 separation constants are there. So separation constant. So in this way you can just solve the complicated partial differential equation by using a separation of a variable method. You can easily convert the partial differential equation into ordinary differential equation, and you will get the solution by solving that ordinary differential equation. You will get the solution of that partial differential equation. Okay. Now this is another example. Okay. So by using separation of a variable, you can easily convert the partial differential equation into the ordinary differential equation. Okay. So here Helmholtz equation we have to convert into the ordinary differential equation, but our Helmholtz equation in given in spherical polar coordinate system. So here one hint is given over there. So Laplacian operator in spherical polar coordinate system is given, already given. You have to just put the value of Laplacian operator into the Helmholtz equation and just find out the ordinary differential equation for this Helmholtz equation. So in the similar way, you can find out again the Helmholtz equation in spherical coordinate system. So here is again the example 3. This is for the just for homework. So you can just solve. This is for the just practice purpose and just find out the ordinary differential equation for Helmholtz equation. So here is the Laplacian operator in cylindrical coordinate system is a given. So just try to solve the both the coordinate system, spherical coordinate system and cylindrical coordinate system. Okay. So thank you. Okay.